Do you study science?
Yes, I do. I'm a planetary geologist by training. So I got my I did my undergraduate in planetary science at Caltech, and then my master's and PhD in planetary geology at Brown University. And what that is it's basically studying the geology, the forces that shape the surface and the interior of a planet, but studying it not of the Earth, but of other planets. So I spent many years studying ice on Mars, especially mostly looking at the polar deposits of Mars to try and understand how the climate has evolved in the last few million years. Also glaciers that were once upon a time at the equator of Mars, or right off of Olympus Mons. And then as time went on, I got more and more interested in the spacecraft operations side of things. So I sort of reinvented myself as an engineer, and I work in spacecraft operations on the science team to get the scientists and the engineers to work together. So I kind of act as a bridge and a translator and a facilitator for them.
Is there natural friction between scientists and engineers when it comes to outer space travel?
Yeah, they have just different priorities and different perspectives. So the scientist wants to get the best possible data to answer their questions. The engineer wants to keep the spacecraft happy and healthy. And those two things don't always go together. So engineers are really happy to try and go the extra mile to get science, but they need to sort of understand why. Is it worth putting in extra time for this? And the scientists need to understand the fundamental constraints of the spacecraft. So we don't want to break the spacecraft to get good science. Scientists are always really pushing the technology of the spacecraft really to its limits, pretty much whenever possible. And so there is a natural friction there, but everybody ultimately has the same goal, which is to have a successful mission. And so you just need some people who can sort of be the glue and pull folks together.
Which do you find more fulfilling, being a planetary scientist or now reinventing yourself as an engineer?
I find it's called science systems engineering. So I find being this facilitator and bridge more fulfilling because I get to make the science happen, and that has an impact across a broader swath of science topics. I really love hearing from the scientists what they have learned, what I have helped enable, which has included things like discovering the ocean underneath the surface of Enceladus, a lot of stuff on Mars from, I worked on Mars Reconnaissance Orbiter for many, many years, and the data from that is just sort of a hugely fundamental piece of the science community. And most recently, I've worked on the Perseverance mission since about late 2012, early 2013. So I worked on the science definition team. So as we were deciding what was the science that we wanted this rover to do, I was helping sort of shepherd the conversation and the discussion. And so for a period of time, the entire rover was basically a set of PowerPoint slides on my computer. And now it's an actual rover on Mars collecting data every day. And I saw it through from that beginning, and then representing the interests of the scientists that are all around the world, being a person at JPL in the conversations with the engineers, saying things like, oh, if you're going to make that decision, we need to make sure it's going to probably impact or have an effect on this particular instrument. We need to make sure that representatives from that instrument are in these design conversations. I helped I helped design the operations process, the way in which the scientists and talk amongst themselves. If you put 5 scientists in a room, you have 7 ideas on 7 opinions on what you should do. And so I worked to how are we going to have the discussions and figure out a consensus of what we should do each day with the rover, but also what planning software tools do we need, and then working with the programmers and the interface designers to say, like, okay, we need a targeting tool. We need to be able to see the images, in a 3D projection. We need these different instrument teams are going to use this. They're going to need particular types of information to make their decisions, and it needs to talk very smoothly to the rover planners, the people who are actually putting the arm down on Mars or driving to places on Mars, and helping with the testing of that, and just really sort of trying to build the framework for operations and then train the scientists and get them to all come together. So I just really love that kind of work. And then I like that, seeing the beautiful data that comes down, the really awesome pictures, and then listening to them just discuss what they think it might be. Like the stuff that we're seeing, is this what kind of, is this a volcanic rock? Is this sedimentary rock? Is it from a lava flow? Is it from mud deposited by a river or in a lake? And like listening to how hard it really is to tell the difference between those sometimes on Mars, and just sort of being along for the ride as we build up this picture of what Mars used to be like.
If it's a sedimentary rock though on Mars, is there water there now currently?
No.
So wouldn't it fossilize or something and turn into something non-sedimentary?
A sedimentary rock is just fundamentally pieces of rock that have been broken off from somewhere and traveled by wind or water to a new location and deposited, and then slowly compressed to form a solid rock. So that's like mudstone, sandstone, things like that. A volcanic rock, depending on the conditions that it forms in, it can it'll have little crystal grains from the different minerals growing, and by the what kind of crystals and the size of the crystals can tell you a great deal about the conditions that it formed in. But the thing is that on Mars, all of the original rocks are volcanic, so you have little pieces of volcanic rock broken off and traveling. So even your sand, like the chemistry of your sand is going to be ultimately match a lot of the volcanic rocks.
Okay.
And it's just that you might see that it's got more interactions with water along the way if it traveled via lakes and rivers and things like that.
You mentioned something about 5 minutes ago. Insolidescence?
Did I?
I'm saying it wrong. What is it? It was something that was discovered, or it was a vehicle or something. I totally am pronouncing this wrong. You said it in passing, and I wrote.
Well, just our context, please, because I'm not getting the.
I wrote because it was in a science. Statement.
Oh, Enceladus. Enceladus is thank you. Enceladus is a moon of Saturn.
Okay.
It is, if you ignore the sun, it is one of the brightest objects in the solar system, and it turns out that it's this little moon. It's if you just sort of the diameter of the moon actually is less than the width of the United States. It's not that big.
It's a tiny place.
It's a tiny place. It is the surface is covered in water ice, and it's really fresh water ice, and that's why it's so bright. So it's very reflective. And what we discovered with the Cassini mission to Saturn is that there's a plume. It's like a geyser of water coming out of the South Pole. And so we were trying to understand so first it was like, wow, this is amazing. We've got a geyser coming out of the South Pole. Oh my gosh.
A geyser with water?
With water ice. Because you're so far out there. It's so cold, it's immediately ice. And so how does this happen? Okay, there must be liquid water involved somehow. And so ultimately what we figured out is that it's a layer of water ice, and then underneath that it's liquid water, and then there's the solid rock
But there
of
is
the core.
liquid water.
But there is liquid water. And it's probably because of the gravitational pull of Saturn. It causes tidal forces. So just like on the Earth, the moon causes tides, and we mostly see that in the water, right? Your ocean tides. But there is a very, it can have that same effect on rock. It just doesn't move as much because rock is a stiffer material. But if you are able to have a great enough pull on your rock, so it just basically is squeezing, you're squeezing your rock a lot as it moves around, and that can cause heat. And so it has a little, there's a number of moons we've discovered out in the outer solar system around Saturn and Jupiter that have this, the tidal effect has caused water just under the surface, so the frozen surface of the moon. But then there's also Io, which is one of the moons of Jupiter, and it's actually got huge volcanoes because of the same effect, this tidal forces from the planet. But what I was part of with Enceladus, one of the ways that you figure out what the interior is made out of, and if there's liquid, you look at the gravity, and how does the gravity respond? What are the gravity measurements that you can get, and what would you expect for something that size? And you can figure out, how much is solid and what kind of, and if there's liquid at all, or if it's solid all the way down. And so we needed several flybys we needed to do a flyby through the plume, like having Cassini fly through the water plume with its radio antenna pointed at Earth, so that we could get the radio signal to figure out the gravity. And we needed it to not be on the thrusters to stabilize the pointing, because we needed to know what was the effect on, of Enceladus, on whether it was speeding up or slowing down, and how did that change as the spacecraft flew past Enceladus at the South Pole. But we didn't know how much force the plume would be pushing on Cassini, and that's where, so for science, yes, we want to point at Earth. We want to get this radio measurement. And the engineers are like, well, we don't know how strong the plume is. You might push on it and cause the spacecraft to tumble. And that's really bad. So we want you to do it with the little thrusters to stabilize it. And we're like, well, then there's no point in doing the measurement. We can't get the science we want out of it. So my job was to first understand the science that we were trying to do, and then take it, because when you're a lot of the technical experts in any field, they find it difficult to communicate in the broad strokes, right?
You mean common language?
Yes.
Okay.
So I needed to listen to all of these scientists who are talking in technical scientific terms, and then say, okay, here's my one slide summary of why this is amazing and why this is our only opportunity to do it and what we want to do. And then take it to the science leadership of the whole mission, and they say, yes, we support you. And then go to the engineering leadership of the mission, who say, oh my God, what are you doing? And so then I say, okay, we all understand now that this is really important. What are some creative ways that we can come up with a compromise to allow this data to be taken? And we did a number of things, but one of them was, so usually when we do flybys of this little moon, we spend a lot of time moving the spacecraft in all sorts of different directions to take pictures over here and pictures over there. And there's a lot of cool things to look at any given moment in the Saturn system. So we said, for this entire 2 days, we promise not to do any of that. We will just point you. You tell us the good orientation of the spacecraft, so that as long as we can get the radio to talk to Earth, the rest of the orientation, how like that, whatever is the safest, whatever is you think is going to be the the best one, and we promised to do that, and they said yes, okay, you can, but we had to keep 2 plans running much later than usual. One was was other kinds of measurements, and one was this plume measurement, while we were trying to collect information from other flybys about how much was this plume going to push on the spacecraft. So we had to use the planning tools in ways that they were never designed for. We had to keep some of the scientists who were like, but surely we can put, surely we can just a couple hours looking over here. And had to be like, okay, engineers, yes, like somebody's going to have to come in and work on the weekend on this. Are you set so that it takes you the least amount of time? You ready to go? And we all had to, that was my job, was to work out these negotiations and then see them through, and to be like, no, you can't sneak this 2 hours of other observations in. We promised we're going to just do this. And we made it all work. And so, that flyby is just one little portion of the complete collection of data that was needed to tell us that it wasn't, that Enceladus, it's not just like a little pond of water at the south. It's actually a whole ocean around the entire planet. No, liquid underneath the surface. But it took a lot of different data sets, but I'm really proud of my little portion that led to that result. Well, maybe. It's a good place it's a place we're really interested in for life, because what you've got, if you think about on Earth, the deep sea smokers, they're these sort of vents, these columns, right? And then vents right at the water rock boundary, and you've got all sorts of really interesting life that uses that chemistry to drive their metabolism. And so we could say, we can think, oh, maybe there's something like that at Enceladus too. That would be really cool. And then you have the plume sort of spitting out bits of ocean. And so maybe if we really study the plume, maybe there's little bits of organics and things that could tell us more about what's going under the surface without having to drill down.
Did you always want to study space?
Yeah, pretty much. There was a period of time I got really into, so I grew up, geology was a family hobby, and this idea that the rocks around us tell the story of what the place used to be like. My grandfather worked in an iron mine in Minnesota, and he would bring back interesting rocks for my dad, and that got my dad into geology as a hobby. And then I grew up being like, oh, look at what we're driving along, and here's the road cut, we're in upstate New York. Look, there used to be an ocean here. And then later there was 2 miles of ice when the glaciers came through. So, and then when I learned that you could do that, but for other planets, that was just amazing. So, yeah. I'm a big fan of stories. I love learning this. I love history. I love, especially the stories of the past. And geology is it's the story of the past, but it's also a puzzle, because you have to translate from the rocks to what are the environmental conditions. And then it's also a mystery, because half of the pieces are missing, because you've got erosion. Yeah, and they can't talk. So it's fun.
So we've talked about what you were doing, Cassini and things like that. What are you doing that's upcoming?
I am actually on a little I had some medical stuff, and then also my son is in middle school, and so I'm slowing my career down a bit to take some time for family and health, and then we'll see what happens in a couple years when I want to go back. But what I had been doing most recently, so earlier this year, was working as a disaster coordinator, which makes it sound like, you know, you pull out your planning book and you're like, what kind of disaster would you like today? But what it really is every time there's a disaster somewhere around the world, relief services like FEMA or World Central Kitchen or, you know, their equivalents in other countries will often come to NASA and say, what do you have any information from satellite information that could help us? And so then NASA sends out to representatives at each of the NASA centers, who then contact the scientists and say, hey, what do we got? And so I did that for JPL for about a year. So for example, Hurricane Ian in Florida, we did a lot, and also the earthquake in Turkey most recently, we did a lot of taking radar data from before the event and then comparing it to radar data after the event, and doing a comparison of the two to look at where are there changes. So it was where had buildings collapsed, and then sending that information over so that relief aid workers could know, okay, there's an area where it looks like there's been a lot of damage. Let's make sure we send somebody out there to check it out. So that's what I was doing up until, you know, just a couple months ago.
What about the planetary geology of Venus?
Venus is super cool. Venus is very hard to study because it's got such a thick atmosphere. It's very hard to see the surface in optical wavelengths because of the chemistry of the atmosphere. So we have done a lot, you know, back in the 80s and early 90s, there were some missions that studied Venus. We think that, so Venus is about the same size as the Earth, and it's got a lot of, looking at basically the shapes of the surface, we know that there's been a lot of volcanic activity. Basically, the whole surface of Venus is very young. We're seeing a very young surface. There's not a lot of impact craters. We have several missions going to Venus that are in the planning stages. One of them is a JPL mission called Veritas, and it's going to, there's been some evidence as people are looking at some of the older Venus data. There's some thought that maybe there's active volcanoes there, and so this mission is going to map the surface in higher detail than before, and use that combined with some gravity measurements and things to try and look for to see if there's any volcanoes there. Unfortunately, because of the way, you know, NASA gets their budget from the government, and then they divide it up into, like, here's going to human space flight, here's going to astronomy and astrophysics, and here's planetary. And then planetary says, okay, we've got the entire solar system, and the entire solar system's super cool, very interesting. So now we have to figure out how we're distributing the money amongst the missions that are currently going places and the ones that are in development. So Veritas, unfortunately, like they're being pushed back a bit. They were going to launch, I don't remember what date they were going to launch, but now they're kind of like, okay, we got to put you on hold for a little while we spend money on these other missions, including one of the big things with Perseverance is collecting these samples to bring back to the Earth, and so we need to fund all the missions to go get the rocks and bring them back to Earth, and that's a huge undertaking.
Perseverance is on Mars again, isn't it?
Yes.
Okay.
Is there any water or storms on Mars?
Well, there's water as solid ice today, we think from studying the rocks and the chemistry of the rocks on Mars that about 3.5 billion years ago, there were lakes and rivers and maybe even an ocean on Mars. So we think like long ago there was water. There's a chance that there was ancient life on Mars, which is what Perseverance, that rover, is there to study. But today the atmosphere is really thin, so you don't have storms, you don't have rain, you don't have storms the way that you might think of them, but we do have dust storms. So we just get a lot of dust in the atmosphere, and every so often it actually goes around the entire planet. From the orbit, you can't see the surface. There's just so much dust in the atmosphere. And that's actually how we lost Opportunity rover. It was solar powered, and there was so much dust in the atmosphere that it couldn't see the sun, and it ran out of power. It ran out of power to keep the heaters running, and it died.
So now it's just floating in space?
It's sitting on. It was a rover, so it's just sitting on the surface.
What surface? Mars?
Mars.
Mars?
Yeah, we have several. There's several rovers and landers that don't work anymore that are sitting on Mars.
How many rovers did you send to Mars?
We sent Pathfinder, we sent Spirit and Opportunity, and then Curiosity, and now Perseverance. And right now, Curiosity and Perseverance are both still working.
But I thought you send rovers to Mars to collect samples.
So Perseverance is the most recent rover, and so it's studying an area that we think used to have a lake and used to have a river going into a lake, and so we have been collecting samples as we've been exploring this area.
Testing it out.
So we're collecting data with like cameras and different. They're called spectrometers. They're instruments that look in different wavelengths, different kinds of light, to study what the rocks are made out of. And then when we find some really interesting rocks, then we drill them and we put a little piece of rock in a sample tube, and after we've collected some, we place a bunch of tubes on the ground, and so that another mission comes to pick them up and bring them back to Earth. Because what we're thinking ancient Martian life would have been bacteria, it would have been like algae or pond scum kind of stuff. It would not be, anything that had bones. So we need to look for really subtle clues and like patterns in the chemistry of the rocks and the, microscopic shapes in the rocks to really figure out if there was life. And that's the kind we need a big laboratory to do that. We can't take the laboratory to Mars, so what we're trying to do instead is take Mars to the laboratory.
Do the rovers have cameras?
They have a lot of cameras.
Like there's like TVs in NASA and they can see what the robot sees?
It's not like movies. It's we take a bunch of pictures and then send them home at the end of the day, kind of thing.
How do they get back to Earth?
So the rover has a radio dish that it talks to. There's an orbiter that's flying overhead, and it talks to the orbiter, who then they save it, and they send the data to Earth, and we have giant radio dishes in Canberra, Australia, and Madrid, Spain, and then in the Mojave Desert in California, that all spacecraft, all out in the solar system, use to send their data back to Earth.
So
and
it's
that's
like
we talk.
boosters that like boost themselves to Earth, or
Yeah, it's like I don't know if you ever now turn on a radio in the car, like let's say your streaming service isn't working, you can't get Spotify on your phone, and so you're like, okay, fine, we'll turn on the radio. That's the same, so that's picking up the information to turn into music from a transponder somewhere that's radiating out the radio. And so that's essentially what we're doing, except that instead of it being like a little dish sitting on top of a building somewhere, it's actually a robot out in space. So we need really big dishes to hear it. And that's what we call it, the Deep Space Network.
For a final question, what would you say to the younger generation that wants to get into the science fact field?
It's really fun. I think a lot of times culturally we think that things like art and literature is just fundamentally different from science and math and engineering. And the thing is that they both require creativity. And so there's actually a lot of back and forth between them. Because it doesn't matter how good your idea is or how good your problem solving skills are if you can't explain your answer to others. And so, I think that knowing that it is this creative undertaking, and that sometimes the best thing to do if an opportunity comes your way to do something, to learn something, and you think, oh, that seems really hard, like it sounds cool but it seems really hard, to just try it. We all make mistakes. Sometimes making mistakes is your best way to learn something new.
Beautiful. That was
Awesome.
Great. Right over.
Yes, I do. I'm a planetary geologist.